day, so that we can see focus on representations of the quantum channels, the mathematical representations of the quantum channels. And I'll wait until Mikel has this. Can you tell me more or less here? Okay, it's enough. This is. So, okay, let's remember that quantum channels are these evolutions that open quantum systems undergo. For example, when you perform some measurement or some stochastic interaction with the environment, with a classical environment, and so on. And they have three main properties. Okay, so quantum channels are linear operations. Lineal or linear? Linear. Linear. Yeah. Yes. I was just suddenly confused with that. Okay, so they are also. Oh, of course, they are quantum channels apply on density matrices, not on pure states, because in general the state of an open quantum system is a density matrix. So they are linear. They are choice preserving. And they are completely positive. Okay, so quantum channels transfer a matrix ρ into some other density matrix E of ρ. Okay, this ρ is a bounded operator on an input Hilbert space, and this is a bounded operator on an output Hilbert space. So the channel is this transformation from one set of density matrices to the other. In order to the map to preserve the properties of density matrices, we need these three properties, that it is linear, trace preserving, and also completely positive. So this is the summary of what we saw the previous day, mainly. So I guess the most, not strange, but maybe the less familiar property is how to check complete positivity, or what is complete positivity, or how do we characterize complete positivity. And before starting with representations, I would like to comment on that. Okay? Yes? What is the B? Okay. So B denotes, B of H denotes bounded operators acting on the Hilbert space H. So B of H, yes, is the set of operations that go from H to H, bounded operations, yes? So bounded means that a bounded object in the input is also bounded in the output. Okay, you can think also of, this is a subset of, no, it's not a subset of, yes, it's a subset of mappings from the Hilbert space to itself. Do you need an example? Because that can be difficult for me right now. It's not on. Yes. Yes, for me it was difficult because I'm focusing on finite dimensional Hilbert spaces. Okay. Okay. So that's the thing. Then I wanted to explain our complete positivity. Okay, so in order to characterize complete positivity, let me introduce first the maximally entangled state. Okay, so a maximally entangled state is a state of a bipartite system. Okay, so we have two subsystems, A and B, with associated Hilbert spaces, HA and HB. And a maximally entangled state is an state in this subset, which has all of the Smith coefficients equal to 1 over d. So it's okay, so both A and B are d-dimensional, and the maximal entangled state has this form. So it entangles the state J in A to the state J in B. Yes? And this is maximal entangled. So the nice property is that once you have fixed a basis to describe your maximal entangled state, you can construct any other maximally entangled state by performing only local operations. Okay, so any maximally entangled state phi that could be expressed in some of the bases with, let's say, phi E, in some of the bases, can be written as a local transformation of a canonical or a reference entangled state in this form. Okay? So this is nice because in principle one would suggest to perform the operation in both substates in order to transform this JJ into a C phi J or something like that. But it is sufficient to transform only one of the local parts because those coefficients of the transformations can be combined. Let's say.
Sorry, I know. Phi is a normal state or also maximally entangled?
Phi is some of the basis for this Hilbert space. Okay, so J here denotes like a canonical basis, a basis that we use canonically, and we assume we are working on this basis in general. And this 5i of E is another, is some basis of this HA or HB. Okay, so in general, any maximal entangled state can be written in this form. And if we, yes.
Omega and phi are the same state but in a different basis.
No. Yes, they are similar, but they are not the same state. They are different states, but they are maximally entangled, each of them in a different basis, but they are maximally entangled in.
Okay.
So, yes.
Yes.
You're saying that this state is maximally entangled, but you could say the same from a GHC state, and this is not a generalization of the GHC.
A GHC state, you mean in a bipartite system?
You can build a GHC state for d dimensions.
But we are working on a bipartite system. Now I'm talking about about bipartite systems with equal dimensional bipartite systems. This is a maximally state of a equal dimensional bipartite system. So there are only two subsystems, A and B, and both of them have dimension D. So in this context, we can define the maximally entangled states always in this form, and any maximally entangled state can be written as a local transformation of this maximally entangled state. Yes, more or less. Yeah. So a GHD state is for n subsystems, but we're only working with two. This is what we need for what I'm going to explain now.
Okay, so it seems to me that it is, so this is a d-dimensional state. If we translate it to qubits, I think it would be a GHC state.
Yes.
I'm not sure.
I'm not sure. I don't think, yeah, but yes, I'm not sure.
So in a GHC state, you measure on the first 10 qubits, let's say, some pattern.
Yes, this is more like a Bell state.
This is tricky, but
yes.
But if we were to think about translating translating this to two-level systems, I'm not sure if the state would be the same as a GHC state of those number of qubits, log of 2 of the.
But the problem is with more than qubits, the concept of maximal entanglement is not
Unique.
unique.
Yes, indeed.
Okay. So what I want to introduce now is that, okay, I'm not going to prove it, but I hope more or less it seems reasonable to you that if I can write any entangled state of this form, maximal entangled state, then I should be able to write any state C of this subsystem with a reduced density matrix on system B of the four of let me okay, so this is rho B is the partial density matrix of the state, the pure state C on the on the subsystem B. Okay, so we have two subsystems, A and B, and here we are tracing out the state in A, and we are left with a density matrix in B, a mixed state in B. Okay, so the joint state of A and B is the state C, and the mixed state rho B is the partial trace of the state C. Okay? So the thing is that for any rho, we can find many states satisfying this relation. The thing is that for all of rhos, we can find a C that is obtained via a transformation on the reference, the maximal entangled state, which has, and this local transformation has this form. Okay, so
Is it any unitary?
this is the unitary. This is a unitary B. Well, it's an isometry in general, but you can think of it as similar to a unitary. This is so this takes care about readjusting the basis where you are representing your state, and this tunes the weights of those states somehow. So that's the intuitive idea behind this. But the important idea is that we can write a purification of any state rho B as a transformation from this state, the maximal entangled state. Okay? So the mathematical part behind this property is not that difficult, but it could take a while. So I just wanted to share this property because it's important then to prove complete positivity, the relation with complete positivity with this state. But, okay, so we have introduced a maximal entangled state in a canonical basis. Okay, we have seen that all of the maximal entangled states can be related with the maximal entangled state in a canonical basis via unitary transformation of only one part of the state, of only one of the subsystems.
So phi is another maximal entangled.
Yes.
But
But yes, more or less. Another maximal entangled state? Yes. And now, but with a different Hilbert-Smith decomposition. Then, what we see is that any density matrix in one of these subsystems has a purification psi, okay? And which can be related with the maximal entangled state in a formula similar to this. But R is no more a unitary operator, I think. It's not a unitary operator, but has some properties that allow us then to prove a relation between this maximal entangled state and the complete positivity.
Sorry,
So,
what is the thing outside the
This is a V. It's an isometry, similar to a. You can think of it as a unitary transformation.
So it's a what?
Isometry. I don't know if it's isometry or isometry. Isometry means that it preserves the norm of the associated space. Unitary. Yes. So a unitary transformation, for example, is an isometry.
I will bother you also. Can you repeat the line of thought of all connected?
Yes.
Please.
Maximal entangled state?
Yes.
Yes. Another maximal entangled state always can be related with this maximally entangled state by a unitary transformation of one of the local parts. Then, any density matrix of one of the local parts can be written as a purification of the joint system. I have shown no proof about that. Just, does it seem reasonable to you or not?
Can you repeat the phrase?
Any density matrix, rho B, can be expressed as a as the partial state of a purifier of a pure vector state in a duplicated system, in a dilated system. And now there are many doses, many states that satisfy that the partial trace is this rho B. Okay, at least one of them, there is one of those states can be shown to satisfy this relation with the maximal entangled state. Okay, so this state somehow can be used to generate all the density matrices in one of the subsystems. Okay, that's more or less the idea behind this. You don't need to understand like it in a whole. Okay.
Okay, but how did it jump from? I mean, in the previous step, you had a rotation on one of the sides, which allowed you to get another pure state. But now you have a weird R, which is not a unit.
Yes.
You are not expecting to understand.
You are not. I'm not. No. I have the explanation here, but I think if we enter it, I will get confused, and I don't think we will have time to arrive to anything. Okay?
I just want to understand from that.
Because I have not explained the jump. So this was.
R is not
R is not unitary, but has, due to this structure, where rho B is a positive Hermitian matrix and V is an isometry, due to having this structure, it's enough to then prove results about complete positivity, which is what we want to see.
Does rho depend on the previous side?
No, rho B defines psi. Doesn't uniquely define psi. But this expression.
Because the idea is that you have certain mixed state. That's all. And every mixed state can be purified by enlarging the Fourier space. Okay? This is the point. And this way of writing, the one that behind right now, is a purification. Any purification of rho B can be written in this is a very powerful. So writing in rho B state C constructed in this way is a purification of rho B. So now if you take C and trace out the A part, you will recover rho B.
I can enter into details if you want. Ahora sonará el tren.
V is always the same, but it depends. For example, if you are state, you want to recover
V, I think V also depends. Yes, it adjusts the different Hilbert bit basis. Yes. V also depends in rho B. Yes.
So this is just a way to say, okay, I can invent a pure state from a system
which can be related to the maximal entangled state. So the important part here is this, yes.
Then that right to this relation
the partial
between
trace
size
maximally
and
entangled state
maximum
of the maximally mixed.
Yes,
What is the trick?
because yes, if R was unitary, then the resulting state psi would be the maximal entangled state.
No, there exists.
Well, would be a maximal entangled state. Then the trace would, this rho would be the identity, the maximally mixed state. So R cannot be a unitary, of course. And if rho b is the identity, you can see here you will have the identity, which is V multiplying V, and V would be, instead of being an isometry, would be a unitary with some with this D. Okay, so more or less, yes, that's true. So if psi is a maximal entangled state, then R can be a unitary in this case. In that case, yes, and rho b would be the maximally mixed state. Yes. So the idea here is that equation. So I will leave.
Maybe to prove that this is the most per general one is quite complicated. But maybe you can show that if you trace out the B for the C, you obtain a B.
If you mean, yeah.
It's up to none.
I'd rather keep on moving, or if you want, I can stop here and explain the two properties of the maximal entangled state that prove this result, but I don't think it's worth. You mean computing the trace of this?
No, to see that if you trace out the A subspace of CT,
Okay.
you obtain O B, but it's in one line.
Yeah. Yeah, but well, line the blackboard. Okay, so if we write. And we are tracing, well, in this case we are tracing B, but yes, we are tracing A. That's true. Okay. And now, due to the trace property, we can use the cyclic property to put this here. No. Well, this is the identity.
You need to write omega as the definition.
And then, what's the one-liner?
If you write omega in this definition, the one that you then you have the trace of J. And then you have the identity in the middle.
Is R line the same as R transpose?
It's only
So the trick about the R is that it's also trace person. Because
every unitary
R is it only has norm 1. And with that is enough to say that the right-hand side is split as
the trace of layer A is the delta IJ. That's all.
This. What do you mean?
Because you are tracing out of the first short space. So you have identity ij, identity. So this trace is just the delta ij.
And now this is the remaining the state that we obtain in the end. Yes?
Yeah, because you are getting the partial trace, not the total trace. So when you rotate
We are yes. I missed this. Yes, I apply the trace in B again in my mind. Okay.
so you have R, one related to R.
This is. I mean, I just want to be explicit in the sense that you have the traces applying the projector here. So you have R, E, R, J, I, dagger times K times J and I times K. So these are delta Kj and delta A. So these two have to be the same.
Did you just trace over A? Why do you have two sums? Oh wait, never mind.
Yes, I have all of the sums, but they disappear with this.
Okay, okay.
And now if we write the R here,
No, the sum over K is identity.
this sum over K can go inside, yes. This was D, B. Okay, so as this is an isometry, this is one, so this is identity, and then this with this, you get rho B. Because this is Hermitian, so D with D and D goes out, and this with the Hermitian with the other part, you obtain rho B.
Why did you write Ruben dagger?
This is just to be emphatic on the sense, but it's the same. Yes, rho B and rho B dagger is the same because it's Hermitian.
But it's like outside of the square.
The dagger,
If it was
yes, it's outside of the square root, but the square root, like, right? No, no, nothing here.
but the square root is not unique. So you can, well, I don't know for the scientific if it is unique or
No, but the square root is not unique, but square root times a square root always makes the same matrix because the square root is defined in that manner.
was saying that the daggers on the other side. So that's a difference.
Yes.
It's not like the square root of the Roby dagger. It's like the square root of some operator that coincides with the square root of just to be annoying.
Okay. Yes. Where's my took? Okay. This is the part that I wanted to skip, yes, but there is no problem with this. If you need it, you need it.
I have one question before you finish raising your hand. Just the last line.
I
That's
would-
okay, that's okay. So the last line, in the last line, you have applied the previous equation, or are you trying to prove it? The equation that we wrote before has the square root of d and rho b. Are you trying to prove it, or are you applying it?
What equation? Well, I don't understand.
You have a square root of d times rho b, right?
Uh-huh.
Okay, and previously you said you established a property between psi and omega, where r was defined as something with that square.
Uh-huh.
Okay, are you applying that thing, or are you proving it?
No, we are applying it because R is defined. So this is not a proof of the statement. This is just some reasons so that you see that the statement makes sense. Because if you trace out the other path, you get this.
Okay. Yes.
But it's not.
Because I told you said it so that if you take this definition of privacy, then you can go
Yes.
not the opposite, but not necessarily, but
Okay. All right. So I think the previous day I told you something about a property that characterizes a complete positivity, which is that positivity in general means that for any positive operator rho, the image is also positive. Okay? So that means positivity. Positive. Yes? Okay. So complete positivity means that in general, if we dilate this operation to a larger system, and so now T acts from some H to other H prime, and now this thing acts from some H extended with something that is n-dimensional to this, with the same image with some extended thing. It means that if where ID is the identity map, okay? So this means that now instead of considering just your quantum channel isolated, now you consider you have another system where you do nothing. It's the identity. This other system is n-dimensional, okay? Then the map that you create by considering that evolution should also be completely positive for any. Okay? So this is a channel that goes, the one above, goes from H, a quantum system, to a final quantum system. Okay? And this map is positive if for any positive operator here, you get a positive operator out there. Okay? Now what we are considering is that what happens if to this channel, whose evolution you have described with this map T, now you append some other system which is n-dimensional in general, okay? And this other system evolves with the identity because you do nothing here, okay? Now, any operator that you take in this joint system, the image of any operator that you take there should also be positive out there, okay? So if you consider you append a system where you do nothing, then the channel must still be positive. Okay, so in general, that's not being positive is not sufficient to being completely positive. Okay, so for example, the trace operator, and there are other operators that don't satisfy that property. Okay, but quantum channels must satisfy that property. But the problem here is that in general, you may think that you have to try for any possible n. So any system that you append should satisfy that property, but proving that property for any possible n is like a very big task. So we will see now a characterization that reduces the problem of checking, of verifying complete positivity. Yes?
Why the, I guess that is Hilbert, but why do you prime the Hilbert?
Why?
Why do you put a prime?
Because the input and the output Hilbert spaces do not need to be the same. So for example, a quantum channel can be the partial trace, where you discard a part of your channel, and the input quantum channel and the output quantum channel is not a quantum channel. Quantum systems, they are not the same, so they don't have the same Hilbert space.
Okay, and why is the other part not trace? Oh, that's it.
This other part,
Yes.
because this is a system where you are doing nothing. If you are doing nothing on it, you cannot change the Hilbert space describing it.
Okay.
Because if we put here a m and in the other part an m, then you cannot do the identity. You have to do something that changes from one dimension to the other. So we have n to n. Yes? Okay, so the interesting property here, and here we will have the help of our new friend, the maximally entangled state, is that it's sufficient to prove that this property holds for this case. Okay? So what is this first? Okay? So this T with the identity in D means that we have a map, we have appended a new system that has the dimension of the input Hilbert space. Okay? So this Hilbert space, the input Hilbert space has dimension D, the output Hilbert space has dimension D prime, okay? And what we have done is to append a map, or to delete our original quantum channel with another channel that goes from a d-dimensional Hilbert space to a d-dimensional Hilbert space. Yes? Nothing here. Okay, now the maximally entangled state that we saw here can be an input state of this joint channel, because as this is a d-dimensional system with another d-dimensional system, this is this instance, we can define the maximally entangled state in this input system, in this joint system. Yes? Now, then we can apply the deleted map, which is the original quantum channel with the identity map, to this maximally entangled state. And it will evolve to some output state. Yes?
Now, why you don't do this if you append not any possible space, but another space? Because this C space.
This C space is a d-dimensional Hilbert space. It's isometric with a d-dimensional Hilbert space. So this C space is just simply to denote that it must be a Hilbert space that is d-dimensional. So we could have written another H here. But I don't want to mix things up by using the same notation to things that are not strictly the same. Okay? Yes, but that was a good question. Okay, so the thing here is that the state that you obtain in the output completely determines the positivity, the complete positivity of your original channel. Okay? So if the output state of the maximally entangled state is positive, then the quantum channel is completely positive. This is what this characterization says. Okay? I have not explained why.
No, but so greater than equal to 0 or only greater than?
Greater than or equal to 0.
Equal to 0, then also is completely positive. Yes?
Yes. Yes, but this is the thing that the difference between taking something strictly positive or positive or equal to 0 thing. So yes, if it is equal to 0 is positive, you are taking positives as positive things that are also equal to 0. In general, we are taking those things. But yes, for this to be 0, I think. But yes, okay. So this is the problem.
The inequality above 0 means that all the eigenvalues are above 0, right?
Yes. If your operator is diagonalizable, if you can diagonalize your operator, it means that all the eigenvalues are above 0. If not, I'm not sure. They can be 0, yes. Greater or equal to 0 means eigenvalues are greater or equal to 0. The thing is that if an operator is positive, if for any state this is positive.
This is only for the condition of the values. It's only if the matrix is Hermitian.
Positivity can, I think positivity can only be defined for Hermitian matrices. Yes, in this sense, yes. So being positive means so this can only be defined for Hermitian matrix, I think. Yes. I guess using this property, maybe you can generalize it to other things, but usually when I speak about positive operators, we are considering that they are real, that they are Hermitian. Yes.
Yeah. So this is not what we want to mention, that the condition of the eigenvalues is not enough for any matrix to be semi-definitely positive.
No, but there are metrics which are not Hermitian and they are diagonalizable real space. So it's a sufficient condition, but not necessarily.
Yes. Okay.
I have another idea of question. So in this block, are you trying to prove the positivity, or will you use the positivity and show something fun?
In this block, I wanted to show that complete positivity can be characterized with this property. And characterization means if and only if. So T is completely positive if and only if this thing is positive. And I have made this stop here to explain what this state is. This state that's completely positive, because this state is the Choi-Jankowski matrix state, okay, that we won't have time to see. But the important thing, I'm happy if we arrive at till this point and more or less it's understood. Yes, what this means. I mean, this is a joint map acting on the maximal entangled state, and the output state, which is a very big density matrix, which has lives in this d prime times d dimensional space. That matrix is the Choi-Jankowski matrix. Okay? Which is very related with many properties.
One question.
Yes, please.
One question. This one is very quick.
Okay. No problem.
So you are using T parameter identity in a channel, right? And you are applying this channel in all that state, or are you multiplying these two stuff together?
I'm applying that channel to a state. Yes, the other thing makes no sense.
What we matrices, right?
No, this is an operator. So these are not matrices yet. These are operators, in a sense. So this acts on this, and if you describe this as a matrix, it's much bigger than this other matrix. Well, this not exactly, but yes, yes. Okay. So if you are interested in the proof of this one-to-one relation between the positivity and the complete positivity and so on, you can look at it in the internet. And I don't think it's worth that we keep going because we won't have time to reach any milestone. So I think we can leave it here. No, it's no problem. But we will have a third seminar. Maybe if you are interested in this. Okay, so thank you.
Thank you.
And see you.